Okay, hello. Grab a seat. Yes. Close the door, you mean? Yeah, we can. Thank you. Okay, so what I'm going to show you today is actually a story. It's a sad story, actually. It's a bit sad to me, but okay. And I named it, so this is like a Harry Potter and the, I don't know, the Goblet of Fire. So this is Instrumentation, which is this little guy here. It's a little tool. And the Pitfalls of Abstraction. So I will skip this. I will just leave this slide for when it's online. But I will just directly start by telling the story, which is that we were wanting to build dynamic analysis. Yeah. So a kind of exact dynamic analysis, like dynamic call graphs. So we wanted to have a call graph of a program, or to have code coverage, profilers, different kind of profilers, so time, number of calls, I don't know, other kind of things that you can imagine. So we got a student, Bastien, that is not here, that started working on this. And one of the techniques that we started using was method wrappers, or something like that. Yeah, so I don't know if you know method wrappers. I will just give a high-level overview. But this thing is from the 90s, from John Brandt. Actually, the technique that I am going to show, it's not the thing that John Brandt did in the 90s, because we are going to use something that was made afterwards. I don't know actually who did it, but which is object as method that is in the Faro VM by default. And I'm going to explain a little bit how can we use this to do some instrumentation. Yeah. So I hope everybody knows how method lookup works. Yeah. So the idea, I will repeat it just in case. So we have an object that is sending a message to another object. Yeah, so we are saying that this is the sender, and this is the receiver, and this is the message. And when we send a message to an object, we are going to look up the method in the class hierarchy of the object. So we fetch the class of the object, and then we look in the method table or method dictionary, or if we have a method for that selector. Otherwise, we go to superclass and so on. Yeah. So, and each of these things, pentagons are methods, and then these are classes, and so on. Okay, so this works. If here we do this, we are going to start the lookup from here, and then we are going to go here and fetch this method M2. Yeah, right. So that's easy. So how does an object as method work? Instead of a method, we put an object, any object, that is not a method. We put it here, and actually what happens is that the virtual machine, when it will do the lookup, it will find this object, but it cannot execute the object because it's not a method. It doesn't have bytecode. Yeah? So what it's going to do, the virtual machine, is to send the message run within to that object with some parameters. So it will send as argument the method that is going so the selector, the arguments, and the receiver object. Yeah? So like that, we can do stuff. So the question that we had with this student, with Bastien, was how far can we get with this mechanism? Yeah. So just okay, let's try it. We knew that we could build stuff. Actually, code coverage was traditionally implemented like this in Faro, but we wanted to push it a bit further. So we started by okay, what is the first method proxy? The simplest one that we can do. So we can implement a normal class that implements this method run within. And then what we can do is to do something every time that the method is going to be executed. So we are going to enter here, then we are going to do something, and then we are going to forward the execution of the original method, yeah, the one that actually was there before. So the method proxy will actually wrap an original method, and we are going to trap the execution, do something before, forward to the original method, then come back, do something when the method returns, and then return the result. Yeah. So I will show how this works with the picture because it works better than this. So imagine that we want to instrument factorial. Yeah, I chose factorial in a completely arbitrary way because everybody here knows factorial, and I don't know how to. I don't have to explain it to you. So what's happening here is that we have a doit, and the doit is going to send factorial to some object. Yeah, so 17. I'm going to send factorial to 17, and the mental model that you need to have to understand how these proxies work, how these object as method works is that actually we're going to trap the message in the middle of the execution. So we are not, actually the factorial will not directly get executed on top of 17. It will be trapped before. And we are going to call our proxy, the run within method into our proxy. Then we're going to do our logging. And then we're going to forward the execution to the original method. Yeah? And this original method will then execute in the 17 object. And then we can continue executing with factorial of 16, which will eventually do the same, and so on. Yeah? So we are actually, every time that there's a factorial message, we're going to stop everything, call our proxy, handle the things that we want to handle, and then continue. Okay. So okay, we instrumented factorial. We can log something before and after factorial. So far, you follow me? Yeah. So let's go get a bit more hardcore. Yeah. So what else can we do? So the next thing that we want to do is maybe, okay, what I want to know who calls add in sets. Yeah, why not? So I want to instrument set add. And I put a proxy on set add. So every time that somebody sends add to a set, I want to trap that. So then we have a do it. And in our do it, we send the add message to a set that we created before. We trap that. And then we have this run within that is going to be sent to the proxy. We're going to log something. Yes. Now, what I didn't tell you before is that the log is actually inside using another set. And then we are going to send add to that other set. And what happens there is that that set add, by default, will also, that message will also get trapped by the same proxy. Yeah? So it will get stopped in here, in the middle of this execution. And we are going to send run within, again, to the proxy. And then we are going to, I don't know if you see it, but actually we are going to just loop around this thing. Yeah? So this will create an infinite recursion, which, just to put it in name, it's meta recursion, because we are actually recursing on the meta level on the instrumentation. Because actually what happens here is that the instrumentation is getting instrumented too. So, okay, that's a problem. We need to get to deal with that somehow. Of course, this is a simple instrumentation. If the method proxy just calls add directly, that's easy to catch. But if we are calling something more complex, then it's probably more difficult to understand where the problem is. Yeah? And of course, if you want to handle this right now, following the run, if you just use run within by yourself, you have to manage this problem by yourself. Yeah? So the burden of handling this problem is on yourself, the developer that is doing this kind of proxy. Okay, so how do we solve these meta recursions? So we have this scenario. One way to solve this is to understand that when we are jumping here to the run, from the run within to the proxy, we're actually in a different kind of place. Yeah, so this is the instrumentation zone. And inside the instrumentation zone, we don't want to have a recursive instrumentation. Yeah? What we want is that every message add to a set inside the instrumentation zone just pass by and gets executed normally. Yes, that's what we want. Yeah? So we need to implement support for this. One easy way to do it is to put a flag. Okay, but of course that is not so easy. We need to also handle stack and win, for example. What happens if you have a non-local return? You need to be able to unset the flag when there's a non-local return or when there is an exception. You have to also think about concurrent access to your object. So if the proxies share between different threads, suddenly, well, that will break everything. Maybe we can do some concessions to simplify the models, like, okay, we cannot proxify the proxy and wrap methods in the instrumentation. I don't know. But again, building all this, it's on you. It's on us, on me. Yes. So, actually, we started looking at these things, and one of the kind of lessons that we learned from this was that the language, so Pharo and Smalltalk in general, so run within is not originally in Smalltalk, but we have done not understand, and other hooks that got introduced during years, like cannot interpret. So they give us kind of low-level instrumentation hooks. Yeah, we can do a lot with that, but actually they suffer from these problems, from these meta recursions, from these concurrency problems, and so on. So actually, if we want to do proper instrumentation, they are not at the right level of abstraction. So only if we really want to do simple stuff. But as soon as we want to do something a bit more complicated, they are not enough. Yeah? And covering the gap between these low-level things and what we want to do to instrument is on us. Yeah? So this is the proxy we have. Let's imagine, yes, this is what I showed you before. Actually, what we want is probably something more similar to this. Yeah, we want something that is stratified. What does it mean to be stratified? It means that we want to separate, yeah, the layers. So we want to have two different objects in there, not just one proxy. We have to have two different objects with two different responsibilities. So we want a proxy that is managing the infrastructure stuff that the user doesn't have to deal with. Yeah? So this guy is going to handle the meta recursions, the concurrency, and all the stack and win, and all that kind of stuff. And then we needed some other object, like we call it a handler. Okay? And here we are going to implement our concern. Like, okay, if we want to build a call graph, we are going to implement it in one of these. Yeah? And like that, we can split these two problems, and we can share the infrastructure concerns between many proxies. Yeah? So, of course, this is nothing new. If you follow a bit how proxies work in the wild, so for example, Mariano worked a lot on proxies a couple of years before, and there's also a lot of work in proxies in JavaScript, in Java. So these ideas are not new. But following these ideas of proxies and stratification, so we sit for a couple of afternoons with Steph. I don't know if Steph is here. We built a method proxy library that is safe. Yeah, so it's there. So it's a safe library that manages all these concerns for you. You don't have to deal with that. And based on that, our student later, Bastian, built a method profiler that can count how many times a method is invoked and how much time is spent on that method. And like that, we can do stuff. Okay. In the middle also, he unified some parts of the instrumentation layer between these proxies and metalinks and stuff like that. So there is also some infrastructure things that are moving on, that are being moved in Faro. But OK, so we have something that is working. We can actually use it. And OK, I said, OK, let's get a bit more hardcore. So what else can we do? Now I have a safe instrumentation library implemented on top of Run Within that does a lot of stuff. OK, and I want to instrument the compiler. Why not? Yeah, I want to see where the compiler spends time doing stuff. And this should be safe, so it should not actually do recursive loops, and I don't know. So we have a profiler here, and what we are going to say to this profiler is, OK, I want to intercept all the methods, all the method executions in these packages, in Opal compiler and the parser. Yeah, so here inside the RB parser package, we also have the AST. So every time that we are going to traverse the AST, we are going to know it. And then we're going to profile something interesting, like, I don't know, recompiling the entire integer class. Yeah, all the methods in integer, I want to know if I instrument that recompilation, where actually is the time spent. Yes, and of course, as soon as I do this, it takes a long time. Yeah, so, and that brings me to the second part of my talk. So we have something that works, but it's super slow. So what is the cost of these abstractions that we started adding? So we added safety, and we added abstractions to separate concerns and so on. What is the cost of that? Yes. This second part of the talk are kind of the advances. So we are still not where I would like to be, but OK, how are we actually moving towards something that gets useful? Yeah. So I started to think about OK, how can I check what is the cost of this thing? And I said, OK, let's profile and let's benchmark Fibonacci. Yeah, I don't know. That's another arbitrary choice. Why not factorial? Actually, because Fibonacci looked to me a bit more interesting. Yeah. So first, Fibonacci is a good case for the proxy because it kind of has it always goes toward through the happy case, the happy path. Yes. So it doesn't have no local returns. It doesn't have exceptions. It doesn't have meta recursions because I'm not going to call Fibonacci in the instrumentation. And it doesn't have concurrent usages by default. So, okay, this will actually measure the happy case, which is actually maybe something if we can optimize for the happy case. Yeah. Also, one thing is that Fibonacci will somehow simulate a big call tree. Yes. So it will give us some idea of overhead there, of what happens when we have a big call tree by just instrumenting one method. So I can run an experiment really easy. And one thing also that is interesting here is that if we look at the leaps of the execution of Fibonacci, actually what they do is just to do a fast check. So they do an if, and if the receiver is smaller than 2, then it returns an 1. So it's actually a fast path. And there we are going to see a really high overhead. Yes? So it's like here we are simulating really small methods, which is actually the case. So here we are going to see a lot of overhead, and that is what I wanted to see. And also one other interesting thing to see is that Fibonacci of n is actually giving us an idea of the number of messages that actually happen during the execution. So that means that, okay, I can actually use the return of this as a proxy to understand how is the overhead regarding the number of messages. So by just running Fibonacci. So now I have Fibonacci, I instrument it, and what is the first thing I should measure? So my first thought was, okay, let's measure the lower bound. The simplest thing that I can measure is run within. So just what happens actually when I just do run within without anything else? Yes, what is the overhead of doing this? So having a run within method that just forwards the execution, but that doesn't do anything else. So it doesn't do any instrumentation. Yes, so that kind of will give us an idea of what is our minimal, our baseline. We are not going to get better than this, except if we change this instrumentation mechanism. Yeah. So then I did this and running it. I ran this with Fibonacci from 0 to 28 because that was running sufficiently fast during my vacations. And here, actually, what is plot is the relative performance. So in blue, in dark blue, what we see is no proxy. So no proxy installed at all. So just Fibonacci. And this is 1. And this is the number of times that is slower than the baseline. Yes. So the unsafe proxy, I'm going to call it because it's the unsafe version. Actually, we see that at the beginning, it is 15, 20, it arrives at almost 25 times slower. Yeah. So we see that somehow this looks to be a bit faster for smaller arcs, so for a really low number of messages. But maybe that is due to noise because we are doing I did the measurements in microseconds, not in nanoseconds. So, but okay. But I told you that Fibonacci is kind of a proxy of the number of messages. So what if instead of plotting it like this by the Fibonacci argument, I plot it by the number of messages, so which actually will give us a different scale. And that gives us something like this. So actually, this is pretty constant. Yeah, so yeah, we are in 25 overhead that is consistent. Yeah, so I can actually say that yes. In my machine, this has this overhead. I cannot tell what happens in your machines, but this is in my machine. So of course, if we want to get better than this, we need to change this run within stuff by a better mechanism, probably in the VM or I don't know. But if we cannot get better if we don't change this mechanism. Yeah. So now I know how bad is the unsafe version. So now the question that we could ask ourselves is how bad is the safe version? Yes, the safe version that manages all the other mess. And if I plot that, yes. So of course, here I didn't do any optimizations, but OK, so we can, again, I am plotting against the number of messages. But here we see, again, a kind of a trend. So yes, it's between 2,000 and 3,000 times slower. This is kind of not acceptable. So that means that, yes, we can use this to instrument Fibonacci of 20, but we cannot instrument an interesting program. Yes? So Why is this? So first, if we look at the implementation of our safe proxy, we see that, yes, it uses non-clean closures, which means that every time that there's a proxy execution, we are allocating closures that actually need the context. So the context is reified too, so that is overhead. We are having a lot of messages because we have ensure to manage the stack and win. We have also all the messages for meta recursion control, the before and after hooks, and so on. So yes, that could explain somehow this high overhead. Now, I spent a couple of days, let's say, doesn't matter, trying to optimize this. So, and how can we do better? Actually, I got it down to 400 times, from 3,000 to 400. Okay. The main optimization here that I did is just inlinings. So I just removed abstraction. So I removed hooks from the program. So I didn't have any more dynamic dispatch. I removed dynamic dispatch from the program, and I got down to 400 times. So I removed messages, I removed blocks. I also made a nice optimization differentiating the fast path and the slow path. So if I assume that the common case is that we are not going to have meta recursions, we are not going to have concurrency, we can probably go have a fast path for that and then a slow path handling the other cases. Okay. Now, I wanted to also measure what is the overhead of call tree, so constructing the call tree. And here what I did is to have actually two different proxy variants. So the first one is the one that has a handler object. And the second one was, OK, what if I inline the handler inside the proxy? So we go back to the implementation where everything is together and it's not stratified anymore, to remove messages. We could think that we could have a proxy compiler that actually I can give the handler and the proxy, and it builds me a proxy that is optimized. So if we had that, OK, this could be that version. Yes. And then I had two instrumentation variants. One that was the one that was built by Bastien. That was an online instrumentation that, while the program is executing, it's building the call tree. Yeah, so it has a lot of overhead to build the tree during the execution of the program. And I had a separate one that is just delaying the construction of the call tree for later. So I am just tracing the minimal information that I need, so putting it into an array. Every time that I enter a method or exit a method, I trace that information. And then I will post-process that big array, or actually a set of arrays, to rebuild our call tree. Yes, and I'm going to use as comparison baseline to compare both these four variants, the safe with optimization, so the one that was 400 slower. Yes, with no instrumentation, so doing nothing. Because actually here what I want to do is to measure how much overhead do I have in my instrumentation, not by the proxy. So here you have the plot of the four. Actually, these are 4 of the 5, because the generic proxy with the handler with the online was actually off the charts. I couldn't even finish. I didn't want to. I wasn't patient enough to let it finish, actually. Maybe another day. So I let it off the presentation. So what we see here is actually the blue line here is the baseline. So it's the proxy, the safe proxy that has 400 times overhead. And all of them are just relative to that one. So here, when we are talking about 2, it's 2 times this one. Yeah. So here 2, it means 800, and 8 means 1600, and so on. So what can we see in here? Actually, both of these two, the yellow and the orange, actually they are the delayed analysis, and they look like some 20-something% slower than the baseline, while the other one is actually around 6 times. So 6 times 4, so it's 2400 slower. So this one is the one that I don't like. So which is the online analysis. Okay, so delaying the analysis can get us better. Okay. Now, what if we make a zoom there, and we just take a look at a bit more detail and removing the other one that is off the charts also. So we don't care. So here, what we see is that a customized proxy, so actually a proxy that doesn't have any hooks, so just having one object for the entire proxy, versus a generic proxy, is slightly, yes, there's one that is slightly better than the other one. Actually, the specialized is slightly better, maybe 0.8 less than 0 to 1%. So I don't know. But they are around 25%. Yes, so this is 25%, so 25% of 400, so we are at 500 times of overhead from the original program. We can think, okay, maybe this is satisfactory or not, depending on the application we want to instrument. But okay, I said, okay, let's stop here and go back to instrumenting my compiler, because maybe here now it's practical enough to do it. And of course, when we are actually instrumenting the compiler, we are not instrumenting the entire program execution. We are just instrumenting the compiler code and the parser code. We are not instrumenting, for example, collections that are in Faro or other methods that are in the kernel library of Faro. So this is kind of a partial instrumentation. So at the end, just doing this gives us a whole overhead of 12 times around. So here what we see is that this is the baseline, so running this code without instrumentation. This one here is the original time. So it's the instrumentation without any of the optimizations. And here we see the instrumentation without all the optimizations that I did. Yeah? So we could get down from 110 times to 12 times. Yes? This is a sad story because this story is going to stop here today. So of course, we are open to enhance this and make other kind of analysis and design other kind of solutions. You can actually think like, okay, what is the future of this? I don't know. So this is the books that leave an open ending. So this is an open ending. But there are some things that we can actually learn from here. So we need a way in the language, in the programming language, to have safe, stratified, and efficient instrumentation. Yes, we are not there yet. Also, we saw that the low-level hooks that we actually provide, they are not enough. So if you are building your own proxy implementation, think twice maybe, or maybe it's better to join forces between many other people to do it, because it's not an easy job to actually do this. So you can do it safe, but maybe not efficient, and you can do it maybe efficient, but not safe, I don't know. So it's good to actually join forces there. So thank you very much, and I hope you are not crying. Yes?
I'm not sure I understand why it's sad.
Yeah, because I wanted better. Yes, it's a matter of expectations. Just that.
What was the question?
He was not sure why it was sad. Because I had high expectations. Yes?
Did you consider like editing the bytecode or like decompiling, inserting callbacks, and then recompiling and then running
Yes.
the code you want to instrument?
Yes, but I wanted to see just the run within, how far can it go? Yes, so I could also run many other different kind of experiments. I didn't do it because I didn't have the time. But yes, I'm not convinced that will have better performance. Probably slightly better, but it will reduce the original, the baseline overhead that we are going to have. Marcus.
So if you look at meta links, they try to be a little bit better by not having the method wrapper there all the time, but by inlining kind of like the message sent directly, which of course does not solve all problems, but it adds a little bit of possibility of optimization, I guess.
So if you, one of my, I don't know, I talk to myself, you know. And when I talk to myself, I say, okay, we have this mechanism, and it's only useful to do simple stuff like collecting coverage. So I keep asking myself, is it worth to have this mechanism if it is not efficient and it's not practical? So maybe we need to go full meta links at some point or something like that. I don't know.
Meta links are in some way just a generalization of method wrappers that you can wrap around every AST
Yes.
construct.
With more granularity, but yes.
But the problem is that the efficiency problem is there the same. I mean, the recursion control destroys
Yes.
Did you have, if I remember correctly, the unsafe was 25x slower?
Yes.
And we guess that most of the time goes in the run within.
Yes.
So I was wondering, since that is in the VM, it's not in the image side, did you have the chance to sample profile where the time is spent in the run within and see if maybe a more efficient mechanism could be applied instead of the run within?
So, no, I didn't have the time. We can do it outside if you want. So if you want, to me, my hunch is, it's not a hunch, but actually what happens when we have a run within is that, let's see the happiest scenario. We are in JIT code, yes? So we are in machine code. We are going to send the message send. It's going to go through a peak. And if it goes through a peak, it's just a call instruction, yeah? So and the problem is that when we have a run within, the call instruction is actually not bound to a method because there's no method. So it has to call to a trampoline that jumps to the runtime. It has to take what is in the stack because the arguments are there. It needs to allocate an array, put the array, so what was before one instruction, now it's many more instructions. So that is the overhead, if you want. Okay. Thank you very much.